Hey everyone, it's Mr. Glover here. So today we're going to talk about conditional probability, dependent and dependent events. Up until this point, we have spent some time talking about different ways of calculating probabilities. And last class, we kind of took a bit of a step sideways, and we talked about some different types of events. We defined what are called mutually exclusive events. And the idea is that if things are mutually exclusive, they can't both happen at the same time. So today we're going to talk about some different types of events, something called dependent and independent, as well as something called conditional probability. And the idea here is that sometimes events impact the likelihood of other events, while sometimes they don't. And we have to treat them differently depending on the context of the question. So let's get started. Last class, we learned that events that aren't mutually exclusive can impact the probability calculations. For example, find the probability of drawing a 10 or a spade from a deck of 52 cards. So if we wanted to solve this, we would need to draw ourselves a Venn diagram. So let's see, these are for 10s, so there's 4 10s. There's spades, which there's 13, and there's one 10 that's a 14 or a 13. Oh, there is one 10 that is a spade. And we want to find the probability of drawing a 10 or a spade. Okay, now since it's 10 or a spade, probability of 10 or a spade is equal to the probability of getting a 10 plus the probability of getting a spade. However, since they're not mutually exclusive, because we do have a number that is both a 10 and a spade, we have to subtract the intersect. So we have to subtract the probability of 10 intersect spade. We can now plug our numbers in. There are 4 10s in the deck, and there's 52 cards. So the probability of 10 is 4 over 52. There's 13 spades in the deck, and 52 cards means there's 13 over 52 is our probability for spades. However, there's one spade that's also a 10, so we have to subtract 1 over 52 to account for that. So in this case, 4 plus 13 minus 1 gets us 16 over 52. And we'll end up with a probability of about 30%, 31% probability. Now, this is a mutually exclusive event situation, or sorry, this is a non-mutually exclusive event situation because getting the 110 of spades could be double counted, and so it is possible for them both to happen. However, whether you pick a 10 or a spade doesn't really matter. If you were to replace it back in the deck, at the end of the day, you're going to have the same probability of drawing a 10 the next time or a spade the next time. So in the situation we're talking about in this question, these are non-mutually exclusive events. If we were to replace the cards we draw, then the probability of any subsequent draw does not get changed. However, if we keep the card that we drew and we go to draw another card, well, now suddenly there's less cards in the deck, and their probability of getting a 10 next time is different. So that is the idea we're trying to build on, is that sometimes, depending on what you're doing, you may influence the probability of a future event by doing something in the present. So let's take a look at this. Today we'll look at another way that multiple events can affect the probability calculation. First, we need to define some terms. So independent events are events whose outcomes have no impact on one another. Usually when people refer to independence, they talk about how they aren't reliant on others. I'm an independent person, meaning that I can take care of myself and I don't need others to do things for me. Same thing with independent events. They do not rely on other events to dictate their probabilities. So flipping a coin is a perfect example. The first time you flip the coin, it's 50-50. The second time you flip the coin, it's 50-50. The third time you flip the coin, it's 50-50. There's no greater chance of getting a tail, even if you flip 4 heads in a row. Um, we've got to be kind of careful how we word that, because the probability of getting three tails then a head is going to be different than the probability of getting a tail, a head, a tail, a head. So it might not be extremely likely that we will get seven heads in a row and then a tail, but that eighth flip is not, you're not any more likely to get a tail or a head based on the previous flip. And that's a misconception many people have. It's called the gambler's fallacy. It's this idea that well, there's no way I'm going to lose again. In fact, your probabilities are exactly the same, so you can't think about it that way. Dependent events, on the other hand, these are events that are impacted by each other. So drawing marbles from a bag would be an example. So let's say that we had well, let's just say this is our bag here. Maybe we had two pink marbles and maybe we had two blue marbles. Okay. So the probability of getting pink is 1 and 2 and 4, and the probability of getting blue is 2 and 4. Okay. Now, if I pull one out and now I've got 3 in the bag, let's say I've now got 2 pink and 1 blue, the probability distribution has changed. I now have a 1 in 3 chance of getting blue, but a 2 in 3 chance of getting pink, and they're no longer equal. So this is an example where one event impacts the probability of a future event. Well, this is an example that every time the probabilities are the same. So when you start doing problems, you need to ask yourselves the question, are these independent or are these dependent events? So let's go through a few examples. Rolling a 5 after rolling a 3 should not depend on the previous roll whatsoever. So because we rolled a 5, the next roll, we could roll a 5 with the exact same likelihood. That tells me these are independent events. After or drawing a 3 after drawing a king. Now this is the important part here, without replacing a card. So the first time we draw a 3, there's 4 3s out of 52 cards. So 4 and 52 is our probability. Once we've removed that though, without replacing the card, now there's only 51 in the deck. So drawing a king is going to, or drawing a 3 is going to depend on whether you've drawn a card previously. So these are dependent events. Drawing a 3 after drawing a king with replacement. So this means we're putting the card back after drawing it. And as long as we maintain that 52 cards in the deck and four of every card, we're not influencing our probability. So these are independent events. And then lastly, flipping ahead after flipping ahead. Flipping the first head doesn't impact the second head at all. So these are independent events. Which leads us to the sort of last new concept today, and it's this concept of conditional probability. So the conditional probability of an event it essentially means that once event A happens, the probability of event B may be impacted. So we have to take into consideration that the probability of B after A is different than just the probability of B. So to kind of go back and explain this using an example, let's use this example. In the first case, we had probability of blue equals 2 over 4. Okay. Now, we also had a probability of pink equals 2 over 4. If we go do the same thing on the other calculation, because we've already drawn a blue, I'm going to call this the probability of blue slash blue. And what that means is blue given blue, or in other words, the probability of getting blue after blue was drawn. In this case, we've only got one blue left, so now it's 1 in 3. The probability of pink given blue is still 2 over 4. So we would call these probabilities on the right-hand side conditional probabilities. This is conditional depending on the fact that we've already drawn a blue. And if you look at the actual numbers, they're different. There's a 50% chance that we'd get a blue the first time. The conditional probability of blue given blue is now a 33% chance. So it's this idea that your future probability has been impacted, so we can't just call it probability of blue anymore. We have to call it something else. In terms of the textbook's definition, conditional probability is the probability of an event occurring given that another event has already occurred. It's typically written as probability of A slash B, and what that means is the probability of A given B. Essentially, probability of A, assuming B has already happened. So let's try some actual questions about this. So we've got 6 red marbles and 7 blue marbles in a cloth bag. If Andrew draws a red marble from the bag, what is the probability the second marble is also red? Okay, so let's set up the problem. We've got 6 marbles, or 6 red and 7 blue. 6 red, 7 blue. If Andrew draws a red marble from the bag, so he's drawing a red marble first. So originally, he's going to have the probability of 6 in 13. All right. However, we're going to subtract 1 red. And what that's going to mean is we're now going to have 5 red and 7 blue. This is the conditional part because we've already removed the red. If we want to calculate the probability of drawing a marble now, we have less marbles to choose from, so there's only 12 to pick from. That's going to impact our conditional probability. So the probability of a red marble given that a red marble has already occurred is going to equal 5 divided by 12. If you compare that to the original probability of 6 over 13, we now have different odds. So the probability of red given red is approximately 42%, 41.6%. So these questions are kind of strangely set up in a way. The actual math isn't that challenging. Doing the 5 over 12 isn't the hard part. It's framing the question and figuring out the context and how to actually lay out what numbers get divided by what numbers. That's the tricky part here. Let's try another one. An ace is drawn from a deck of 52 cards. What is the probability that the next card is also an ace? So we've got 52 cards. And we have 4 aces. Okay, so the probability originally is 4 in 52. However, we're going to remove 1 ace. So now we're down to 51 cards. What is the probability that the next card is also an ace? So now we're down to 51 cards with 3 aces left. So the probability that the next card is an ace, which I'm going to call the probability of ace given ace, is now 3 over 51, different than 4 over 52. This works out to about 6%. Probability of ace given ace is 5.9%. However, the other question that's being asked is, what is the probability that the second card was a king? So going back to this example, we removed 1 ace, 51 cards, 51 cards, but we still have 4 kings. And you might be thinking, okay, so drawing the ace does not affect the kings. Well, it does because we still have 4 of them. However, we're now down to 51 cards in the deck. So we're more likely to get a king than we would have been beforehand. The probability of king, given an ace has already been drawn, is going to be 4 over 51, which is about 8%, 7.8%. So It's kind of a finicky type of problem because you really have to be cautious setting things up. If I had picked 52 here, would ended up with the exact same, well, the same probability as we originally had would not be our conditional probability. Let's see, Bob has flipped 7 coins and all of them are heads. What is the probability the next coin is a head or a tail? Well, to answer this question, we just have to recognize that coin flips are independent. What that tells me is that the probability of getting a head, given that there's already a head flipped, is the same as the probability of just getting a head in the first place, which is 50%. And the probability of a tail given a head is the same as the probability of getting a tail at any point, which is 50%. So it's kind of a trick question. However, if I had asked the question, what is the probability of rolling 7 heads in a row? Well, that's going to be a little bit different than this type of calculation. The odds of being struck by lightning are 700,000 to 1. If Matthew has just been struck by lightning, what's the probability he gets struck again? Now, this is the truly tricky question. Lightning strikes are independent events. So the probability is the same. So that means the probability of lightning is still 1 in 700,000, which works out to not a very likely outcome. It's 1.42 times 10 to the minus 4%. It's probably not something you've got to worry about in your lifetime. I mean, you want to take the precautions to avoid getting struck by lightning. I wouldn't go golfing. Well, actually, you won't be allowed to go golfing on a day filled with lightning. I wouldn't run out into a field with a big metal pole in my hand. I wouldn't climb trees, but you're probably not going to get struck by lightning. Sometimes we're interested in finding the probability of a combination of events, and this is kind of where it all comes together here. For example, what if we want to know how likely is it that we draw an ace, then a queen? We know how to get the probability of a queen given an ace has already been drawn, but we haven't talked about how to figure out the probability that both events happen. Okay, and now in order to solve these kind of problems, we have to first ask ourselves, are these independent events or are these dependent events? Okay, probability of A then B is equal to the probability of A times the probability of B given A. Essentially, probability of A times the probability of getting B, but it's now impacted by A. Now, this is only true for dependent events. All right, so I'm going to write 2 formulas here, and I'm going to separate them because I really don't want these to get fused together. The other situation is if we're talking independent events, probability of A then B. If they're independent, it's simply probability of A times the probability of B. And that is it. Sometimes you'll see this written as probability of A and B. It's just the wording of the question. The idea here is that you're always going to be multiplying the probabilities of each independent or each individual event. The difference is that for independent, B isn't unaffected by A. So B given A is the same as B. For dependent events, the probability of B is changed by A, and we have to take that into account when we're multiplying our numbers. So let's try a couple of these. What's the probability of drawing 2 aces in a row? And I should have been a little more careful how I worded this question. There's no replacement. Okay. So in this case, because we're not replacing the cards, these are dependent events. We can kind of write out what we know. So we know there's 52 cards. There's 4 aces initially. So the probability of ace and ace is given by probability of ace times the probability of ace given ace. Probability that we got our first ace is just 4 over 52. However, once we draw an ace, we now have 51 cards and 3 aces, so the probability of ace given ace is now 3 over 51. This works out to about 0.45%. If we had replaced the cards, and in doing so, we've created independent events, it would just be probability of ace times probability of ace, 4 over 52 times 4 over 52. Since we did not replace the card, second ace depends on the first ace. A couple more. A bag of marbles has 4 red, 3 green, and 6 orange marbles inside. What is the probability of Emma drawing 3 red marbles in a row? Okay, so originally we had 4 red, 3 green, and 6 orange, which is 13 total. All right. 3 in a row. I'm gonna write no replacement. And what that tells me is that these are dependent. So if they're dependent events, probability of red and red and red is going to equal probability of red times the probability of red given red. And then the last one's going to be probability of red given 2 reds previously. So I guess I could call it probability of red given red, red. The notation doesn't really matter. It's what matters is what you actually put in for fraction to replace this. Originally, we had 4 reds and 13 total. So the first red marble was 4 over 13 as our probability. However, once we've pulled one out of the bag, we now have 12 in the bag and 3 reds. So the next probability is now 3 over 12. Now we've pulled another one out of the bag. So the probability of red given 2 previous reds is now 2 over 11. Which leads us to a probability of about 1.4%. So I kind of want to go through the idea here because a lot of people will see this and they'll go 1.4%. That's crazy. There's 4 reds. Why is it so unlikely that I'm going to get them? You have to take into consideration that this is only one scenario. If you were to draw a tree diagram, and I don't really want to fill up a whole bunch of space, but let's say we drew a tree diagram, okay? Let's say that we had 3 options for our first marble: red, green, orange. We're then going to have 3 options for the second. And then from each of those, we're going to have 3 options for the third. If you start thinking about how many actual scenarios there are, how many actual individual branches can I go down? I can go red, 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 green, red, 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 green. I have a lot of outcomes. It makes sense that this particular one is not very likely. It's likely that I'm going to get a red the first time. It's not that unlikely I'm going to get 2 reds in a row, but when you start giving criteria like 3 reds in a row or 6 reds in a row. That particular scenario is not incredibly likely. But if you look at all the other options, they all have to add to 100. And so if there's like 500 outcomes, don't expect one of them is going to be 3%. If they're all equally likely, you're probably only going to see like 0.5% each or 1/4% each. What is the probability of flipping 3 heads in a row? So this is the last one. This one's an example where these are independent events. So the probability of head and head and head is given by the probability of a head times the probability of a head times the probability of a head. Each one is 50%. So 0.5 times 0.5 times 0.5 gets us a probability of 12.5%. And so this is the part that I'm trying to get people to wrap their heads around here, is that while the situation of getting 3 heads in a row is only 12.5% likely, if you go to flip the coin, your probability of getting a head here is only 50%. It hasn't changed. Every time you flip the coin, you still have 50% probability that you're going to get into one tail or one head. It's not unlikely that you're going to get a head because you've got a bunch beforehand. It's independent. They don't impact each other that way. However, the probability of getting all of these in a row isn't that likely. So that's the gambler's fallacy that I've been talking about. It's unlikely that you're going to have this entire scenario, but once you've already rolled 2 of them, you're still equally likely to get another one the next time you flip it. All right. Anyways, that's where I'm going to end the notes today. I've got a worksheet for you to try. I'd like you to just do the odd questions. I think it's 1 to 10, so that gives you 5 questions to try for homework. You're going to have to ask yourself for each of these problems: are these independent or are these dependent events? And then you have to determine whether you are working with normal probabilities for independent or conditional probabilities for dependent events. Anyways, so I'm going to end my video. Have yourselves a great weekend. I'll see you all on Monday. And let me know if you've got any questions. Just shoot me an email. Bye for now.